as the table on which the standard reduction potentials of substances are indicated. By now you know that when hot magnesium ribbon is placed in pure oxygen, it burns with a blinding white flame, and a white powder, that is magnesium oxide, forms. During this reaction, magnesium undergoes oxidation and oxygen reduction. Magnesium is the reducing agent, and oxygen the oxidizing agent. Metals are strong reducing agents. Remember, metals tend to rust, which means they are oxidized. Non-metals are strong oxidizing agents. The larger the metal atom, the stronger reducing agent it is, because the electrons are further from the nucleus and are bonded weaker. It undergoes oxidation easier. The ion of a strong reducing agent is a weak oxidizing agent, while the ion of a weak reducing agent is a strong oxidizing agent. The smaller the non-metal atom, the stronger oxidizing agent it is, because the electrons are closer to the nucleus and are bonded stronger. It undergoes reduction easier. The ion of a strong oxidizing agent is a weak reducing agent, while the ion of a weak oxidizing agent again is a strong reducing agent. The strength of the reducing agents and oxidizing agents differ, because the ability to attract electrons or to give off electrons differ. To compare the strength of reducing agents and oxidizing agents, an electrochemical cell is used, where the oxidation half reaction and reduction half reaction takes place in separate cells. Electrons move through the external circuit from the one electrode to the other electrode, because there is a potential difference between the two electrodes. A galvanometer is connected into the circuit to measure the cell potential, or EMF. The cell potential is the tendency of a half cell to attract electrons, and is measured relative to the standard hydrogen half cell, which is used as a reference electrode. To this hydrogen half cell, a cell potential value of 0 volts has been allocated. Because hydrogen is a gas, a platinum electrode is used over which the hydrogen gas bubbles at standard conditions, namely a temperature of 25 degrees Celsius, a pressure of 101.3 kilopascal, and the concentration of the electrolyte is 1 mole per cubic decimeter. Hydrochloric acid or sulfuric acid is used as an electrolyte. Platinum is a non-reactive metal and are used in all non-metal half cells. This reversible reaction takes place in the standard hydrogen half cell. During the reduction half reaction, electrons are taken up at the electrode. Because reduction is taking place at the electrode, it is the cathode. Remember Cre. The hydrogen ion is the oxidizing agent. During the oxidation half reaction, electrons are given off at the electrode. Because oxidation then takes place at the electrode, it is the anode. Hydrogen gas is now the reducing agent. When the cell potential of different substances are measured, they are connected to the standard hydrogen cell, and the other cell must conform to the same standard conditions as the standard hydrogen half cell. Remember, the galvanometer measures the cell potential of the other cell relative to the hydrogen half cell. If the cell potential is positive, it means substance X is a stronger oxidizing agent than the hydrogen ion, and it then oxidizes hydrogen. while X itself is reduced. This electrode is then the cathode, and the platinum electrode of the hydrogen half cell is the anode. The electrons then flow from the hydrogen electrode to the X half cell in the external circuit. The more positive the EMF value, the greater the tendency of the substance to attract electrons, and the stronger an oxidizing agent the substance is. If the cell potential is negative, it means substance X is a stronger reducing agent than hydrogen, and it then reduces the hydrogen ion, while X itself is oxidized. The electrode is then the anode, and the platinum electrode in the hydrogen half cell is now the cathode. The electrons then flow from the X cell to the hydrogen half cell in the external circuit. The more negative the EMF value, the greater is the tendency of the substance to give electrons off, and the stronger reducing agent the substance is. We will now show you how the hydrogen half cell is used. When the hydrogen half cell is connected to a zinc half cell, the E0 value on the galvanometer is minus 0.76 volt. The negative value indicates that zinc is a stronger reducing agent than hydrogen gas. Therefore, the hydrogen ion will undergo reduction, and it is the oxidizing agent. Zinc is oxidized. In this cell, the electrons flow from the zinc half cell anode to the hydrogen half cell cathode in the external circuit. In this hydrogen copper cell, the E0 value on the galvanometer is plus 0.34 volt. The positive value indicates that copper is a stronger oxidizing agent than the hydrogen ion. Hydrogen will therefore undergo oxidation and is the reducing agent. Copper undergoes reduction. In this cell, the electrons flow from the hydrogen half cell anode to the copper cell cathode in the external circuit. The EMF of half cells of various elements relative to hydrogen as a reference electrode is listed on two standard reduction potential tables. This is only a section of a table. It is called the reduction potential table because the forward reactions are all reduction reactions. For this lesson, we're going to use table 4b. It is the one with lithium at the top and fluorine at the bottom. You can also use table 4a, where fluorine is at the top and lithium at the bottom. Whichever one you use, you must use the same one throughout. The reactions on the table are written as reversible reactions. If the reaction is read from left to right, it is a reduction reaction, because electrons are taken up. What is on the left, therefore, is the oxidizing agent. If the reaction is read from right to left, it is an oxidation reaction, because electrons are given off. And the substances on the right, therefore, are reducing agents. The more negative the EMF value, the stronger reducing agent it is. Lithium, therefore, is the strongest reducing agent. The more positive the EMF value, the stronger oxidizing agent it is. Fluorine gas, therefore, is the strongest oxidizing agent. As we move upward on the right side of the table, the reducing ability increases. And as we move down on the left side of the table, the oxidizing ability increases. A spontaneous redox reaction releases energy. For this exothermic redox reaction to take place, a strong oxidizing agent must react with any reaction will take place spontaneously if the oxidizing agent is bottom left and the reducing agent is at the top right. So lithium will react spontaneously with fluorine gas. And the half reactions can be written from the table by writing the substances that react with each other below each other. Now complete the reaction with only a single direction arrow. The oxidation half reaction is the reaction in which electrons are given off. The reduction half reaction is the reaction in which electrons are taken up. Will copper react spontaneously with zinc ions? Look up the substances on the table. Zinc ion is a weak oxidizing agent, and copper is a weak reducing agent. The reaction will not take place spontaneously. Certain substances appear on more than one place on the table, and therefore you must make sure that you mark them all before you can identify the reactions that take place. Manganese 2+ ion. Water with no other elements except hydrogen and oxygen. Iron 2+ ion. Chromium 3+ ion. Iron 3+ ion. Copper 2+ ion. Sulfur dioxide. Copper +1 ion. Hydrogen peroxide. The nitrate ion. Write down the half reactions where iron reacts spontaneously with copper 2 sulfate. Mark Fe. Look carefully. Fe appears more than once on the table. Ionic substances must be broken down into ions. Copper 2+ also appears more than once on the table, but SO4 2- only once. For a spontaneous reaction, the strongest reducing agent reacts with the strongest oxidizing agent. This is the oxidation half reaction. And this is the reduction half reaction. Write down the half reactions when manganese reacts spontaneously with chromium 3 hydroxide. Look up the substances on the table. If a substance appears on both sides, the other reaction will determine whether this substance undergoes oxidation or reduction. Spontaneous means the strongest oxidizing agent reacts with the strongest reducing agent. This is the oxidation half reaction. And this is the reduction half reaction. Except for electrons, some reactions also contain hydrogen ions. That means the reaction takes place in an acid medium. Note, water is then formed. In these equations, water is not oxidized nor reduced. If water is involved with the electron transfer, there may only be hydrogen and oxygen present. If electron transfer takes place between the hydrogen ion and hydrogen molecule, no other substance may appear in the reversible reaction. Let us summarize. The standard conditions for the standard hydrogen cell and the reduction potential table is a temperature of 25 degrees Celsius, a pressure of 101.3 kilopascal, and the concentration of the electrolyte 1 mole per cubic decimeter. You must understand this table and be able to use it. The more negative the EMF value, the stronger reducing agent the substance is in relation to the hydrogen half cell. The more positive the EMF value, the stronger oxidizing agent the substance is in relation to the hydrogen half shell. During a spontaneous reaction, the strongest reducing agent will react with the strongest oxidizing agent. These reactions are reversible, but the half reactions are written with a single arrow, and you must indicate which one is the oxidation half reaction and which one the reduction half reaction. Remember, the lesson is only complete after the test has been written. Use the opportunity to solidify the knowledge.